Hi everyone, welcome back to another video. In this video, I wanted to share with you how I compiled OpenCV 4.0.0 on my Raspberry Pi Zero 2W. I had posted a previous video, and I'm going to put a link here so that you can see the procedure I went through to build the same version of OpenCV on my Raspberry Pi 4. The procedure is pretty much the same on the Raspberry Pi Zero 2W. The CMake command is a little bit different, and in this video, what I'll share with you is the CMake command, and also I'll show the packages that I installed before actually doing the compilation and the procedure. So for the most part, I'm going to rely on the reference to the other video for the Raspberry Pi 4, since the procedure really doesn't change except the CMake part. One more difference is that I do not disable the swap file on the Raspberry Pi Raspberry Pi Zero 2W. I have to run the Raspberry Pi Zero 2W with 2 gigabytes of swap just to be able to get my applications up and running. They typically run on a Raspberry Pi 4, which has plenty of RAM, but here I have to have always a swap file active. So that's one difference also that you may want to keep in mind. Here is the website for the GitHub repo for OpenCV. I'm going to build OpenCV 4.0.0 only for C++, because that's what I'm programming in, and there's a lot of other tutorials and guides on how to install OpenCV for Python. I have to actually install a lot of Python packages in order to build OpenCV, but I personally don't use it for Python, use OpenCV with Python. I'm programming C++. So the procedure that I will show you here might not apply to you if you're interested in Python, but it might work for you as well. I just don't know. So what I will do is I will get the version 4.0.0 of OpenCV that is from this GitHub repo. This is the OpenCV itself. The latest release is 4.5.4, and I know my application works with 4.5.4 on my Windows and also on the Mac OS, but on my Raspberry Pi 4, I'm still behind on OpenCV. I'm at version 4.0.0. That's worked for me, and I haven't had a need to upgrade it. So when I compile my applications on the Raspberry Pi 4, and then I deploy those binaries to my Raspberry Pi Zero 2W, I need to have the matching OpenCV 4.0.0 on my Raspberry Pi Zero 2W as well. The procedure should work with a newer version of OpenCV. I haven't tried it. Maybe I'll do that as a separate video later. But for now, I'm going to stick to OpenCV 4.0.0. But I wanted to point out that it's not the latest version, and but I think the procedure should work. The other repository that I'm going to have to get is OpenCV_contrib. In my procedure, I actually don't clone it. I just go and fetch the zip files for this 4.0.0 release from the OpenCV download page. But I could also clone the 4.0.0 branch or tag from these. You may want to note that there are other repositories here: OpenCV Python, OpenCV Vision Capsules. I don't actually need to bring these two. So the only two that I will get source code from is these two. And this is also shown in the reference video that I mentioned for that, where I actually have the whole procedure recorded. This is some system information. I'm not going to repeat it, but it's here. You can see that there's a 2 gigabyte swap file. So I'm just going to paste the commands for installing the apt packages that from Python, and also the Python modules that are needed. But I am going to quit my VNC because I've noticed that network is unstable on the Raspberry Pi 20W. From time to time, if I'm running an apt update or apt upgrade or some other install, if I have VNC going, it seems like the network might not provide the connectivity in a stable manner, and it might break the upgrade. So I've learned to quit for now. Maybe that'll get fixed. But what you notice is that on the by the way, while sudo apt update or sudo apt upgrade is going on, sometimes also the Bluetooth mouse and the keyboard have lose their connection. And like right now, I'm trying to get the mouse back, but as you can see, it's not moving while the apt update is going on. What you also now have the mouse, but what you see here is the Wi-Fi signal is was not connected, but now it's basically pulsing, and that I'm not sure why is it pulsing, because on my Raspberry Pi 4 it stays steady, and so there are some network issues. Hopefully those will get fixed in the future updates for the Raspberry Pi 0 to W. But as long as I stay off of VNC and I don't try to use the mouse and the keyboard during the apt update, it looks like it can finish in general. So what you are seeing are all the apt packages that I needed to install, not just from Python, but also some other apt packages that are required for a full Python environment, and also a full OpenCV environment for the building of OpenCV. These all should have been installed in the before, because I've already gone through the process. But I'm just listing them, letting them run here to record them for reference and for my own memory. Now, as the apt packages have been installed, installing the Python 3 and Python 2 modules that are needed, and here I'm just upgrading pip, and there you can see the version of Python is 2.7.16, but Python 3 is 3.7.3, and the pips are the latest for the different ones. But now a couple of modules: protobuf, Cython, NumPy, SciPy, Scalearn, and some others will be installed for both Python 2 and Python 3. Although they've been installed before, so it should succeed. But this procedure takes a long time to make sure all these packages are installed. So, but once I go through them, they're good. So the last one that I installed is matplotlib, Scalearn, SciPy, Scalearn, matplotlib. So this is for Python 2, and then I do the same for protobuf for Python 3, same list. Okay, looks like there was a new version of NumPy. So with these packages installed now, there is still more to install. So actually, there's some packages to uninstall, like Wolfram Engine and LibreOffice. I remove these because I don't need them. I don't use them much. So I need the space, I think, more. And then there are more apt packages to install, and I install those. These are for OpenCV compilation as well. So here I am in the location in the folder where I have unzipped an OpenCV 4.0.0 and OpenCV contrib 4.0.0. I've renamed them OpenCV and OpenCV contrib. They don't have the extension in the name after extraction, but within OpenCV directory, I have a build directory. I created a build directory, and this is where I ran the cmake command. I'm going to delete that and redo that step here, just to record the cmake command. So to cmake, I'm saying make a release build, install it in the /user local. This is where the extra modules come from the OpenCV contrib modules. I do want to enable Neon SIMD, and I do want to enable VFP v3 because that's what's available here. I don't want to build the tests, enable non-free, don't install the examples, and don't build the examples. That I don't need those. And then I'm saying go one level up from the build directory, and that's where the source code is found. So I'm just going to execute this. That way, I have it recorded as to what the cmake procedure was. After this, basically, it's inside the build directory. I do make sudo make install, and at the end, I do sudo ld config. This is all shown and recorded in the Raspberry Pi 4 version of this video. But once I've done sudo ld config, the new version of OpenCV is 4.0.0 that I just built would be available. Yeah, CMake was successful in generating the make the build configuration, and I'm just going to scroll back through it. I don't see any issues. It looks like pretty much the same as when I ran it earlier, and it's using GCC 8.30, Python 2.7, Python 3.2, and all the packages that were installed will come into to play here later. I mean, it's going to find them libz, libjpeg, libtiff, the different versions of the things that the app packages that I installed earlier are being found and configured for. So I'm not going to type the actual commands, but the commands would be make on a separate line. I do make, and then when it's done, I do make install. And then when that's done, on a separate line, I do sudo ld config. And that's basically all there is left to do. This procedure for the sudo make install, sudo ld config takes a long time. I actually started it at night and came back in the morning, and it was done. So it's an overnight process, but it happens. It should work. So with that, now I will quit VNC and go to the wireless mouse and wireless keyboard to actually run a program that uses this OpenCV package. So if I run this, it should be able to find the correct OpenCV package. This binary was compiled. I compiled it on a Raspberry Pi 4 with OpenCV 4.0.0. And so here it will, when I run it here, it will look for OpenCV 4.0.0. As far as the setup, I have it capturing from the camera, and it'll do it'll use OpenCV to do a DFT, two-dimensional DFT transform on every on the frames. I'm using ISPC tasks to do the time exposure. This will do a time exposure on the captured images. I tried C++ and OpenCL. There's just not, the ISPC tasks is the fastest time I can get. And I've selected to view the phase information, and I'm using ISPC tasks also to do the phase calculation. And what I'm doing is I'm going to have it not only display the phase image, but also do edge detection with the phase image, but also do edge detection with the central difference method. These are some of the things that I had done on the previous videos on the Raspberry Pi 4. But here I have a basically the scene that's going to get captured. And so here on the right, I have the live color image. This is the time exposure image, which is grayscale. This time exposure, I can only do 5 minutes of time exposure on the Raspberry Pi 02W. Somehow the application is limited in the amount of memory that it can get. So I can only get enough memory off the heap to be able to do a 5-minute time exposure. Whereas on the Raspberry Pi 4, my application is limited to 6 minutes worth of images. On some of the other platforms, my goal is to do 10 minutes because some of the things I want to do with it require a 10-minute time exposure. But for some applications, that's fine. So 6 minutes or 5 minutes or even 1 minute of time exposure is good enough. But that's one difference that I noticed, that my Linux application was limited to, it had less memory available to it from heap. So this is a 5-minute time exposure that I'm calculating. And on the right here, you see the edge detection using the central difference method. And this is edge detection using phase information. So what's happening is that when this image is captured, it's converted to grayscale. The time exposure is computed. And then to do the phase and edge detection with the phase, that involves an inverse FFT. So there's a DFT and an FFT happening on every frame, basically. So all that work on the Raspberry Pi 4, I was able to do that. I was able to do that and maintain a 10 frames per second. But here, my goal is 10 frames per second because I believe that in order to, for some of the applications I have in mind, that is my target frames per second. But the CPU just doesn't have enough horsepower to do all the work that I have done in this application. So it's falling a lot behind. So it's about 5 times slower. It's maintaining about 2 frames per second, but sometimes I've seen it dip down. But the fact that it can actually do this application that was running on, that runs on normal desktop OSs and also on the faster Cortex A72, I'm really happy that I can actually do something, some of these steps. There may be some applications also that might work with lower frame per second. Some things might not need 10 frames per second or more. So I was pretty happy with it. Although the OpenCL device is listed here, I'm not using OpenCL. I'm using OpenCV but the program itself is C++ with ISPC vectorization with a task subsystem that comes with ISPC. Anyways, I hope this information is useful. And again, hope to see you in another video.